Foundation Models for Embodied Decision-Making Agents, episode 10. This is actually almost a repeat. I'm going to discuss an interview with Sherry Yang, who is an author on the paper, Video as New Language for Real-World Decision-Making. I already discussed this paper. It came out of archive a few weeks ago. Sherry gave an interview at one of those machine learning podcasts. I'm going to put it in the show notes. Good podcast, by the way. Shout out to the author there, to the interviewer. Really good, deep, interesting, not too technical, but technical enough. So really good. I just apologize. I don't have the name on top of my head here. So what Sherry's talking about is really, she's making the case for video as sort of the new language for robots, right? And this might sound maybe a little far-fetched for some people. For some people, this might sound like, yeah, duh. I think it's neither, right? I think it's like everything else in engineering. You have to look at it, solve it. There's a lot of bugs to be solved, but the concept really has some legs. Now, what's the concept? By the way, before I go there, I think Sherry is one of those really interesting people because she has this ability to transcend science into technology and even the populace, and I don't mean this in a demeaning way. Not that I mean the populace is stupid and the academics are smart. None of that stuff. But if you work on something for years, you know more about it than a dentist or a cab driver. It's just natural, and I think she actually has this ability to communicate in a very natural way. I attribute this to Berkeley. I think the Berkeley robotics people, Peter Abil and Sergey Levin and Jitendra Malik and many others have this ability. I think it's a culture that I miss in other parts of the robotics community. I find it in Drew Batra at Georgia Tech. So the Stanford people are the Stanford people. Nothing wrong with them. I would say they're a little bit aloof. There's this veil of elitism around Stanford that just bothers me a bit, but certainly people, like Shuren and Chelsea and Pavone and all these people, certainly, top-notch people, no question about that. But I just personally like the approach that Berkeley's taking. But this is a side note. I'm on a tangent. Let's get back to the point. So discussing this interview, which is really a repeat to the paper, right? So the paper that I've already discussed, I think it's a breakthrough in conceptual robotics, because it starts with the idea, how can we have a unified representation of reality and learn from that, right? That's what we have with large language models, a unified representation of reality. We call it text. Whether it's Google Books, whether it's X, whether it's Facebook messages or whatever, even photos, right? Which is just another version of, well, that's not text, but you take text into representation, lower level representation, and then you combine it with video and images, and that's what this unification has allowed large language models and multimodal models to work well. Combine images with caption, combine caption with images, generate images from text. All these transformations are possible because of the latent representation of text and images, and then the model's learning from there and able to generate. Now, the next step is to have videos generated from image caption or actual images or videos. Use this really amazing generalizable intelligence. What Sherry and authors want to do is use generated video for learning. This is the key, right? The idea is, okay, look, we need video, or let's go down the path of video as a unified representation language for robotics, but we don't have enough video. In particular, we don't have what she calls data coverage, right? We don't have, my kitchen is very different than anybody else's kitchen. So the robot learning to navigate in my kitchen might be hard. How can we unify this? Well, one way is to try to find a way to generalize out of people's kitchens and still have a one-shot learning ability once the robot's in the kitchen. That problem hasn't been solved. You have the other approach, which would be to have an close to, not infinite, but massive amount of videos with kitchens generated by video, by Gen AI, things along the lines of Sora, but just longer term video, and then use transformer technology to teach the robot. Within that context, I think we have this recent paper that came out of Waabi, which was talking about using multimodal transformers for self-driving, and I think it fits right into Sherry's discussion. She actually mentions that paper not by name but by methodology. She thinks that tokenization plus diffusion could be the breakthrough that is needed for Gen video to create enough samples for robots to learn. By the way, I'm going to flip back and forth here between self-driving and robotics. Eventually, it's the same problem. Self-driving is a robotics problem in a setting that we call traffic, and robotics in general is just another setting, whether it's a factory, warehouse, or whatever. We consider robotics a distributed computing problem with applications in all kinds of real-world settings. And we consider robotics also a software-defined hardware problem, which is because it's a distributed computing problem, where the compute starts at the edge, goes all the way to the data center. So I think we've spoken about this many times before. This is not the key of this conversation here, because this is not a computer architecture conversation. This is more of a conceptual / model architecture conversation, because what Sherry talks about in the paper a lot is, for example, the denoising, right? Excuse me, that's the Waabi people. But I mean, this is, I think what Sherry wants to mention here, wants to go after, is really what the Waabi people also are going after. So it's very congruent. Okay, we have questions about, let's say, one of the problems would be tokenization, right? And maybe let me now parse this problem into, okay, first, the big picture is we want to create Gen AI, videos, and then learn from the videos, create a data set that is large enough so we can use transformer plus diffusion to generate videos, and then train those robots on those videos, and then solve the sim to real problem, and then go with it, right? That's the idea. On this pipeline, we have several problems, and one is the tokenization itself. How do we even tokenize? And this is from the Waabi paper. We propose a novel world modeling approach that first tokenizes sensor observations, then predicts the future via discrete diffusion. The tokenization happens through LiDAR. So that's why this is an engineering problem, because almost every sentence now is an engineering problem itself. How do you tokenize? Well, do you use LiDAR or camera? LiDAR allows point cloud tokenization, and then from point cloud stable diffusion. So that's possible. What about camera? Well, camera has the RGB pixels. How's that going to work in terms of tokenization, diffusion? So those are questions that haven't been solved yet. So that's why I consider this paper more conceptual, but I think we're on the right path. And this episode, generally, this podcast series, not even a podcast series, is not technical in a sense that we're going to discuss the tokenization problem now, or the pros and cons of LiDAR, although we could choose to do that in a specific paper, but not in this episode. So we're just going to leave it at that. Think of tokenization as a problem in 3D, and think of what to use, what sensor data to use. And then from there, we have the diffusion concept. What is the diffusion concept? The diffusion concept takes images or sequence of images, and then predicts the next evolution of these images. And I think that's the beauty of this approach. We could use some maybe Monte Carlo type evolution of the video. So, and I always like to mention the Harry Potter worlds also. What I mean with that is that we can have my kitchen in a billion different versions, where there is also the one version where I magically touch something and Harry Potter shows up and gives me 3 wishes, right? Maybe that's not, the laws of physics don't explicitly disallow that. And now we're in the realm of philosophy. Anything that's possible under the laws of physics could happen. We're talking multiverse opportunities here. We don't have to go that far. We don't have to discuss Everettian interpretation of quantum mechanics. But what we can do is, we could have a generation function that says, generate versions of my kitchen in a 10-second video that abide to the laws of physics as defined here, X, Y, Z, and just go with it. And I'll give you X amount of time, and you come up with N amount of samples of that 10-second clip. And then within that, we're going to have the robot move around and do some task. This is an example where you're going to get something approaching the multiverse, just by definition, because anything that's possible under the laws of physics will happen. This is one of the statements of multiverse people. And if you do it in sim, in a video generated way, well, that's what you're going to get. And then imagine an off or on policy model-free algorithm that is just running through all these scenarios, and then in an AlphaGo zero type way converges to an optimal way of making coffee, slicing bread, and so on and so forth. And he spoke about, let's start building an infrastructure assuming we have a massive robot fleet that can generate data. Let's think about transformers. Let's think about these things, even though we don't have them. Because here's the big breakthrough that I hope will come very soon. Once we have a base, once we have something that robots can be built on and have a sort of modern robotic sense, meaning we have, let's say, a humanoid robot that can move in a one-shot learning intelligent way, well, those robots then can generate ego data, and we can build on that, right? So once we bootstrap our robotics infrastructure to the point where we can have internet-style data collection, we're out of the woods. Once we bootstrap, the same way the first attempts of the internet before the World Wide Web were very difficult. You would have a hard time coming up with GPT-4 in those days. Once the World Wide Web happened, we were on the verge, but nobody thought about it, right? But we were on the verge of getting there because the data collection started happening at scale. And today, here we are. And this is obviously just the beginning. A few interesting tidbits from the interview. One is, this is a tangent, but it's important for all the full self-drive engineers, the Tesla fans and haters, and it has to do with representation of the picture. So what she's showing is a generated video that was generated from real world videos that robots took. Now, those robots had GoPros on them, or maybe it wasn't even robots. Maybe it was teleoperated by people, or maybe even people. Doesn't matter. But they had GoPros on them. So the robot or the video learned from blurry pictures because what they didn't do is stabilize, right? They didn't use stabilizers such as, GoPro, of course, uses a lot of that stuff, but they just didn't use it. And I've heard some people talk about the FSD and say, well, the pictures there are blurry and stuff. Well, this is why. Because the camera on the car perceives the world in a blurry way because it's not stabilizing. Because I guess stabilization really helps you on sort of a centimeter type precision, which you could argue you don't need, but I guess in the case of Tesla, they have such a large margin of error when it comes to, let's say, circumventing objects that they don't mind not stabilizing a photo or a representation of an object, because those few centimeters of blur doesn't really, it's not gonna make a difference. So this is just a tangent. Back to the paper, back to Sherry and her idea to use video as a language for embodied decision-making agents, right? Imagine the full self-drive problem as an AlphaGo zero type problem set. We want to build a simulated agent that can self-play and go through n amounts of trials in a model-free on-policy RL method, which is very aggressive. That's impossible to do in the real world. That we would never do that, because people would die. But in this case, we could do it. And I believe that's how AlphaGo Zero was trained. And I want to emphasize model-free here. So you're not even making a world model because you don't want to constrain yourself. You really want to be open for even Harry Potter type scenarios. Doesn't matter. As long as they're non-zero and you train enough times, you should be able to converge to a behavior that is pretty close to what we're used to in nature. This could take years maybe to train, but it's possible. And I think that's what Musk meant when he said Dojo could be a massive return, but it's high risk. We could create a foundation model for self-drive and later on for robotics, right? This is what Jensen Huang's talking about when he said we want to become a foundry for robotics. This is exactly what they're talking about. Build a massive simulator agent based on Gen AI, videos with non-zero probabilities for almost anything that can happen, which is allowed under the laws of physics. I think we're talking about something that is a massive compute challenge, also an architecture challenge. This is opening up questions in computer architecture. What kind of training do we even need? What kind of memory, vol clock time? All of these things come up. And this interview with Sherry Yang, the paper, opens the door to that, which is beautiful. And I think we're witnessing science at its best here. It's opening the doors for new science, for new problems, for new ideas. It's gonna hopefully help develop some technologies that then can be iterated upon. And I think to summarize for us as Tesla investors and NVIDIA investors, and we've just made the case in the last episode for a merger, it just cements this idea that if they merged, they could actually accelerate this much faster. We have the compute on the NVIDIA side and the research and development on the compute architecture side, and we have the iteration on the engineering side and the iteration on the model side, which I think is more of a Tesla problem than an NVIDIA problem, because NVIDIA wants to generalize everything, which is fine, but I think it's much easier to first go and solve one concrete problem and then generalize. So again, to summarize, we are incredibly excited about this Berkley paper, that video could be the new language for embodied decision-making agents. We put it in our series for foundation models for decision-making agents because it really fits there, foundation models for embodied decision-making agents. And it fits there because it is the base. It is the base for the foundation models, which starts with generative video, tokenization, transformer technology, this diffusion to generate videos from the real world. And this is where Tesla comes in. Maybe I wasn't clear. I want to bring this point back. Why does NVIDIA need Tesla? Well, Tesla has a lot of videos of real world scenarios, right? Because the idea of Gen AI as a base for video simulation is that we embed it in the real world. And we can certainly create something like ImageNet where we collect a massive amount of pictures, images, and videos of the real world and then train it. But we already have it with Tesla. So if we could create a pipeline where we go from the fleet directly into the video generator and create, the millions of miles driven per day could create trillions and trillions of miles driven in sim. And that's the key. And it's embedded in reality. So you driving on Highway 1 is going to be real. And by the way, maybe this is a tangent, maybe not, but it will also solve, because it's real and because you can iterate around the model how you generate that video, you don't need as much physics because you're just going to learn from what you see. And most importantly, the sim to real transfer will be pretty smooth because you don't need to embed your video generation in physics. It's going to look pretty real, pretty close to what nature actually looks like, and that's going to facilitate the sim to real transfer. Thank you.